In this lesson, we explore different types of symbolic arguments. We start with a couple definitions. An argument is said to be valid when its conclusion necessarily follows from a given set of premises. An argument is invalid, or we can call it a fallacy, when the conclusion does not necessarily follow from the given set of premises. Now, the first type of argument I'd like for us to consider, it's called the law of detachment. The law of detachment. So let me give us an example here. If I say, if we go to the Bahamas, then we will go snorkeling. We go to the Bahamas. Then the logical conclusion that must follow is we will go snorkeling. So if I let P represent the statement, we go to the Bahamas, and then let Q represent we will go snorkeling, then symbolically this argument can be written in the following way. Now take close notes here. Take really good notes. All right, so I'm going to move this up just a little bit. All right, so this is how we're going to write it, folks. All right, first we start with the first premise. Now, this is your first premise. Your first premise is, see if I can write this, if P, then Q. Remember, this is a conditional statement, right? If we go to the Bahamas, then. If, then. That means if P, then Q. So this is your first premise, okay? And then premise number 2 is this second sentence, we go to the Bahamas, which is what I'm calling P. So your second premise is P, okay? And then we're gonna write this like line here that denotes that we're about to make the conclusion. And the conclusion is, therefore, now these 3 dots right here mean, it's like a 3-dotted triangle, if you will, but it's read as therefore. Therefore, Q. This is your conclusion. In other words, we will go snorkeling. So this is how our arguments will be written symbolically. We started with a premise, right? We started with, if we go to the Bahamas, then we will go snorkeling. The next thing that happens is we go to the Bahamas. So our conclusion, therefore, right, is we will go snorkeling. So this is how our arguments will look symbolically. Now, if we want to create a truth table for this argument, then it would look like this, all right? So I'm going to write this statement here, or write the argument in the following form, okay? If P, then Q, right? If we go to the Bahamas, then we go snorkeling. Put that in parentheses. And we go to the Bahamas, right? We go to the Bahamas. That's the next part. If all of this happens, I'm going to put grouping symbols around all of this. If all of that is true, then we can conclude Q. We will go snorkeling. One more time. If we go to the Bahamas, then we go snorkeling. And we go to the Bahamas. Then, or therefore, we will go snorkeling. Let's create a truth table really quickly for this argument. And what I would like to show is that this argument is true. The answer column is true. Now, the answer column is going to be underneath this, under this symbol. All right, so let's do it. All right, you're probably really confident with your truth tables. All right, I have my truth table all set up, ready to go here. I'm going to go ahead and fill in this column right here underneath the if P, then Q. Now, remember, conditional statements are true for every single case except for when the antecedent is true and the consequent is false. Okay, so I'm going to go ahead and fill in this. So this is going to be true. This is the false one, because look at, your antecedent is true, but your consequent is false. That's the only time that happens. So the rest of these will be true. All right. So I don't feel the need to copy down these truth values for P right here, or these truth values for Q right here. I mean, they're right here, you know what I mean? And so I can just reference my P and Q right here. I will copy down my P values here, just to be really clear. Okay, I don't want to make a mistake, and so let me copy those down really quickly. Now, I am now filling in the truth values underneath this conjunction. Now remember, a conjunction is true only when both statements are true. And so this is going to be true here, false here, and false here, right? Because this is the only time when both statements are true. Okay, very good. I think you get that already. We've practiced that a lot. Let me write down my Q statements here, or not my Q statements, my truth values for Q really quickly. So this is true. I'm just copying this over from the beginning of the table. All right. Now I'm looking at this conjunction, like this column, and this column here. Remember, this is a conditional statement, and this is going to be my answer column, all right? So this is a conditional statement, so it's true every single case, for every single case, except for when the antecedent is true and the consequent is false. All right, so let's go for it. This is going to be true, 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 true. So this entire argument up here, which represents if we go to the Bahamas, then we go snorkeling. We go to the Bahamas, then the conclusion is that we will go snorkeling. That entire argument is true for every single case. Therefore, this entire statement here, this entire statement is called a tautology. A tautology, right? Where you get, it's true in every single case. And remember that when you have a conditional statement that's a tautology, it's actually called an implication. So this is also called an implication here. All right, so I want to conclude something very important here for us, and that is whenever we have an argument of this form, okay, if P, then Q, and then we have that statement P as your second premise, then we can conclude that Q will happen. You know what I mean? If P, then Q, and then you're given P, all right, then I can conclude Q will happen, right? This is called the law of detachment. Law of detachment. So whenever we have an argument of this form, then we can make this conclusion. All right, let's look at another example, or technically our first official example. All right, check this out. If the marsupial is taller than 1 meter, then the marsupial is a kangaroo. There's your if P then Q statement. The marsupial is taller than 1 meter. There's P. There's your premise. Okay. Therefore, the conclusion is the marsupial is a kangaroo. So this is your P, everybody. The marsupial is taller than 1 meter. And this is your Q. The marsupial is a kangaroo. And you're given that the marsupial is taller than 1 meter. So in other words, in symbolic form, you have this. If P, then Q. And then you're given the first premise, right? P. Therefore, we can conclude Q. This argument is the law of detachment. Therefore, it is a valid argument because it's a law of detachment. If you can classify, if you can identify that the argument that you're given is an example of the law of detachment, remember this is the law of detachment. If you can identify it as the law of detachment, then you can conclude, I have a valid argument. So we know we have a valid argument here. Okay, the instructions for that previous example and for this one too is determine whether the following argument is valid or invalid. In the previous example, we were able to identify the argument as the law of detachment, so that automatically makes it valid because we know the law of detachment is a tautology. It's always true. So it was a valid argument. But what about this one? If Detroit is in Michigan, then Dallas is in California. Dallas is not in California. Therefore, Detroit is not in Michigan. All right, to get us started, I have labeled Detroit is in Michigan as P, statement P, and Dallas is in California as statement Q. What I want to do, again, is write this argument in symbolic form. Symbolic form. All right, so here we go. This is what we are given. If Detroit is in Michigan, then Dallas is in California. So we have a if P then Q statement. Then what they gave us is Dallas is not in California, so they gave us not Q. And the conclusion that's being made is therefore not P. Detroit is not in Michigan. Okay? Is this argument valid or is it invalid? And if it's invalid, then it's a fallacy, right? So listen, we have not constructed a truth table for this argument yet. So we don't know whether it's valid or invalid. So let's construct a truth table, and we want to investigate all of the truth values underneath the answer column. If we have all true truth values under the answer column, then the argument's valid. All right, let's do it. So what we need to do is we need to write our statement in symbolic form here like this. All right, so if P, then Q, right? And what was given was not Q. So after all of that, the conclusion was then not P. This is the statement that was given to us in symbolic form, and we want to construct a truth table now. All right, so let's do it. All right, I've constructed our table. All right, so let's first fill in the truth values underneath this conditional statement here. And so let me see, change the color here. All right, remember that a conditional statement, once again, is true in every single case or for every single case, except for when the antecedent is true and the consequent is false. Therefore, we have true, false, true, true. The next column I want to fill in is not Q. So I just want to negate all of my Q truth values. So I have false, true, false, true. And then what I want to do next is fill in this conjunction. And now, as a reminder, a conjunction is true only when both statements are true. All right? So I have false, 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 true. All right, next I want to fill in not P. So I'm just going to negate my my P values over here. And so I have false, false, true, and true. All right, I'm ready for my answer column, everybody, which is here. Again, it's a conditional statement. And so remember, it's true for every single case except for when the antecedent is true and the consequent is false. So I'm comparing this column here and this column here. And so here we go. We got true, 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 true. This statement here, the statement is a tautology. But because the tautology is a conditional statement, it's considered an implication. This means that the argument that they gave us is valid because it's true. The argument is valid. Now, this is the form of the argument that they gave us. Let me go back. Maybe I can go back here. Yeah, here it is. So this here, I'm going to highlight it or just, circle it. This argument is valid and it has a special name. It's called the law of contraposition. The law of contraposition. That is the form of this argument. So make sure you have this form, this argument form, labeled in your notes as the law of contraposition. So if you're given a statement, if P then Q, and not Q, then you can conclude not P. All right, we have a new argument that they want us to determine whether it's valid or invalid. Here it is. The grass is green or the grass is full of weeds. The grass is not green, therefore the grass is full of weeds. All right, so let's get our P and Q. Okay, so P represents the grass is green. Q represents the grass is full of weeds. All right, so then in symbolic form, the argument is if P or Q, right? I almost said if, sorry about that. It's not a conditional statement. It's a disjunction, all right? So this is a disjunction. The grass is green or the grass is full of weeds. So they gave us P or Q. And then they said the grass is not green. That means not P. And the conclusion that's being made then is therefore the grass is full of weeds. In other words, therefore Q. Is this form, this argument form, is it valid or is it invalid? All right. So is it valid or is it a fallacy? Again, we've never seen this form of an argument, right? And so therefore we will construct a truth table and then look at all of the truth values under the answer column. If they're true in every case, then this statement is a tautology and the argument is valid. Why don't you go ahead and pause this lesson here, create the truth table on your own, and then we'll move on from there. So go ahead and pause the video here, pause the lesson, create a truth table for this statement. All right, here's my truth table. I'm hoping that you and I both agree. What I discovered is that this is true in every single case. Therefore, this type of argument is valid because it's true in every case. It's valid because we have a tautology. And actually this tautology, because it's a conditional statement, is an implication. So this argument is valid for sure. All right, this form here, this is our next important form, okay, where we have P or Q, and then they gave us not P, therefore Q. This is called disjunctive syllogism. Disjunctive, you can see the disjunction symbol here, syllogism. So from now on, whenever we are given an argument that is of this form, whenever we're given an argument that is a disjunctive syllogism, we can say right away, without even creating a truth table, we can say, oh, we know it's going to be true. We know the argument is valid. All right, this part of the lesson is very important. These are the different types of arguments that we have. We've studied some of them and some we have not yet. We did look at the law of detachment. That is a type of valid argument. And it says if P, then Q. And if we're given P, then we can conclude Q. That is the law of detachment. The law of contraposition, we looked at this. It says if P, then Q. It's another conditional statement. And if we have not Q, then we can conclude not P. Okay? The law of syllogism is another conditional statement. It says if P, then Q. This argument we did not look at. Okay, we did not look at an example of this, but we will eventually. If we have if P, then Q, watch this, and then we're given if Q, then R, then we can conclude if P, then R. I hope you followed that. If P, then Q. And if Q, then R. That means if P, then R. Okay, that's the law of syllogism. Disjunctive syllogism, we did look at that, and that is P or Q, and not P, we can conclude Q. All right, and then we have two fallacies. We have the fallacy of the converse. These are really, really good. If P, then Q, and then that means, and if we have Q, then that must mean P is true. Now, that is not necessarily true. If we have a conditional statement, if P, then Q, and then we're given that Q happens, right? Q occurs, then concluding that P must be true as well, or must occur, is not necessarily true. So this argument is invalid. It's a fallacy. And a fallacy of the inverse would be if we have P, then Q, and then if we have not P, then to conclude then that must imply that not Q. That's also an invalid argument or a fallacy. This type of logic, everybody, is so, so good, and you can apply it in many areas of your life. All right, folks, here is an argument we want to figure out. Is it valid or invalid? Here it comes. If you are on Instagram, then you see my pictures. If you see my pictures, then you know I have a dog. So here's the conclusion they're trying to make. If you are on Instagram, then you know I have a dog. All right, let's get in this case, we have three different statements. We have a P, a Q, and an R. All right, I have P as the statement, you're on Instagram. Q is, you see my pictures. And R is, you know I have a dog. Therefore, in symbolic form, we have the following. If you are on Instagram, then you see my pictures. If P, then Q. The next one says, if you see my pictures, then you know I have a dog. So we have if P, then Q, and if Q, then R. The conclusion they're making then is, therefore, if you're on Instagram, then you know I have a dog. If P, then R. Now, you can create a truth table for this if you want, but there's no need, because if you check out the arguments that we were talking about a second ago, you will identify this, or you should identify this argument as being in the form of the law of syllogism, which falls under the category of valid arguments. Therefore, this argument is valid, and you do not need to construct a truth table. But if you were, you would find nothing but true statements, or truth values, that is, under the answer column. So this argument is valid. Cool. Let's check out another one. All right, we have two different statements here, or two different arguments. So let's look at each one of them separately, all right? One at a time. If it is snowing, then we put salt on the driveway. We put salt on the driveway, therefore, it must be snowing, right? It's snowing. So let's figure this out. Let's call P the statement, it's snowing, and Q is we put salt on the driveway. Okay, so then for the first argument, what form is it in? All right, so let's do it. We have, for the first argument, we have if P, then Q. All right, if P, then Q. And then they told us we put salt on the driveway. So then we're given Q. Therefore, it must be snowing, so that's P. Is this a true statement? Is this argument valid, or is it invalid? Now, this is the fallacy of the converse. The fallacy of the converse. I wonder if I can go back, if I can do it easily. I don't mean to get you dizzy here. There it is. Fallacy of the converse right here. If we have if P, then Q, and then you're given Q, you cannot necessarily conclude P. That's not a valid argument. Again, if you have if P then Q, and then you're given that Q happens, that doesn't necessarily mean that P must happen. All right, so, oops, sorry. Let me go back to where we were. See if I can do that. All right, there we go. There we go. So this is the fallacy of the converse. So this argument is invalid. This argument is a fallacy. In other words, if you have if it's snowing, then we put salt on the driveway. And then we put salt in the driveway. Maybe we put salt in the driveway also when it's raining or something. So just because we put salt in the driveway does not necessarily mean it's snowing. But if it is snowing, then we for sure will put salt in the driveway, right? Again, just because you have Q does not necessarily mean P must happen as well. So this is a fallacy of the converse. This argument is a fallacy. It's invalid. All right, now it's time to look at the second statement here. All right, this one. All right, if it is, I'm going to move the board up a little bit. All right. If it is snowing, then we put salt on the driveway. Okay, hold on. Let me set this up for us. All right. If it is snowing, then we put salt on the driveway. So if P, then Q. It is not snowing, so it is not P. Therefore, we conclude, or they are concluding, we do not put salt on the driveway. So therefore, we conclude not Q. All right? So this is a fallacy of the inverse. So we can conclude that this argument is a fallacy. It's not true. It's invalid. All right? If P, then Q, just because P does not happen does not necessarily mean that Q will not happen. All right? If it is snowing, then we put salt on the driveway. Just because it's not snowing does not necessarily mean we will not put salt on the driveway. Maybe we want to put salt on the driveway for some other reason, okay? So, again, what we're concluding is just because it's not snowing does not necessarily mean we will not put salt on the driveway. All right, so I love all the logic here. It's really, really, it's a lot of fun. All right, this one's kind of crazy because we have 3 different premises. The first one is, if my cell phone company is Verizon, then I call you free of charge. Second premise, I can call you free of charge, or I can send you a text message. Third premise, I can send you a text message, or my cell phone company is Verizon. Conclusion, my cell phone company is Verizon. I don't know about you, but I'm confused. All right, so let's first set up P, Q, and R. All right, so when we have 3 premises here, really what we have is the following. In symbolic form, of course, let's break this up. If my cell phone company is Verizon, that means if P, then I can call you free of charge. So if P, then Q. Next premise. I can call you free of charge, that's Q, or, that's a disjunction, I can send you a text message, so or R. Third premise, I can send you a text message, that's R, or my cell phone company is Verizon, so that's or P. That's another disjunction. The conclusion, therefore, is my cell phone company is Verizon, so the conclusion is P. So this is, in symbolic form, what the argument is. And we're going to have to construct a truth table here. And so really what I have then is if P, then Q. All right, so that happens. And what happens next is Q or R. Q or R. And what I have is R or P. Now, if all of that happens, then I can conclude P. I can barely fit that in there. So this is the truth table that we want to construct. Pretty crazy, right? Let's do it. All right, I have my truth table set up here, and I'm going to start filling this in. So the first one is the conditional statement here. I'm comparing P and Q. So this is going to be true. This is going to be true. This is false. This is false. True, 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 true. The next column I want to figure out is this disjunction here. And so I'm comparing my Q and my R's, all right? So let's do that now. So true, 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 false, true, 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 false. Remember, we want to be very, very, very careful with like lining things up and making sure everything is really neat and organized. All right, next I am going to fill in this conjunction. Remember, a conjunction is true only when both are true. So let me fill that in. So true, true, false, false, true, 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 false. All right, I have my first conjunction. Next, I want to do this disjunction here, R or P. So I'm comparing R, my column for R and P. Remember, a disjunction is true as long as one of them is true. All right. So looking at R and P, I have true. I have true. 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 Okay, good. False, finally a false, true, and then false. Now I can complete this column here, which is this conjunction. Remember, it's only true when both are true. So I can fill this in now as true, 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 false, true, false, true, false. All right, now I'm looking at now let me actually fill in my p-values here really quickly. So true, true, true. I'm just copying these over from that original P column way over there on the left. All right, I got them all. So all I'm doing now is comparing this column here. This was the very last conjunction that I filled in, okay? Here, let me highlight it. Make sure I'm not being confusing here. So I'm looking at this column here and of course my p-values here that I just filled in. And my answer column will be here in this this conditional statement, all right? And so remember that a conditional statement is true in every single case except for when the antecedent is true and the consequent is false. All right, so then I have true, 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 false, true, false, true. So because we did not get all true, we can conclude that, where is it? Way over here, right? Something about Verizon. This statement here, or this argument, is a fallacy. Okay, a little bit of work to get there, but we did it, and we constructed the truth table to make our conclusion. This is our last example, and it's an example of us trying to arrive at a logical conclusion given some statements. So, for example, I will attend the concert, or I will attend the volleyball game. I will not attend the concert. Therefore, so what's the logical conclusion here? We have to figure that out. All right, let's get a P and a Q. All right, I have our P and our Q. The form of the argument is I will attend the concert, that's P, or I will attend the volleyball game, that's Q. So that's P or Q. Next is I will not attend the concert. So they gave us not P. The conclusion then is, watch this, we don't know, right? That's That's what's happening here. Therefore, what should this last conclusion be? Okay. Now, we have to, in order to make this a valid argument, in order to make this true, we have to replace the question mark with a statement that makes this valid, right? So this argument is of the form, do you know it? Disjunctive syllogism. Very good. So therefore, the logical conclusion is, I will attend the volleyball game. So make sure you've identified it as a disjunctive syllogism. So the logical conclusion is, therefore, I will attend the volleyball game.